Okay, so for this particular section, okay, we will be using the VSC code to showcase the various security cryptographic measures that we have implemented into the spam2 system. Okay, so I will walk through, alright. Have to bear with me because we are running both server and client codes. So I will be switching a lot, okay, to showcase how they come together. Alright, so this one will be a very comprehensive client server system that secures the menu distribution, sales data transmission. Okay, we have implemented 4 key mechanisms inside as a form to protect spam2. So the first one will be AES encryption, followed by HMAC. Okay, then it will do integrity checks together with ECC. Not sure if I'm pronouncing it correctly. It's called the elliptic curve cryptography, right? And we also implemented one more, which is perfect forward secrecy. They call it the PFS. Okay, so together they will work together to ensure confidentiality, integrity, authentication, and also long-term resilience against various type of attacks against the spam2. Alright, so I will cover for section 1, which will be the AES encryption. Okay, in both client and server codes, we will use AES -GSM. In the long term is in the full name is called Galois counter mode. So let me just use the code line. Okay, I see where did I put it. Okay, so for this one, hold on, server, wait. Sorry, should be the client side first. I'll start at the client side first. Okay, so the function AES encrypt, which is here, right, takes the sales data and encrypts it with a session key. Alright, they will produce 3 components. I got nonce, random value for uniqueness, okay, the ciphertext, encrypted data, and a tag for integrity check. Here it is, ciphertext, okay, and nonce, ciphertext, this 3, and this is the code that runs them. Okay, so on the server side itself, we have going to the decrypt side. Okay, the AES decrypt, which is here. Okay, it will reverse this process. Okay, it will help to verify the tag to ensure that the ciphertext wasn't tampered. Okay, this one is a very straightforward one. Why we use AES GCM is because it do provide confidentiality. Attackers cannot just read the sales data as and when they like. Also, AES also provides integrity. Okay, if someone modify the ciphertext, the decryption will fail. Okay, this particular system AES is efficient. Okay, it is also widely adapted in modern secure systems. Okay, so to cut it short, alright, I'll move on to the next one, which is the HMAC integrity. Okay, so on the server side, this time around we start server side again. Alright, the function. Okay, wait, where is the function? Hold on. The function. Wait, where did I put this? Sorry, there it is. Sorry, too much code right here. Okay, so by hashing that message, okay, wait, let me just reiterate because just now I was trying to find a code. Okay, so we start server side, right? HMAC. Okay, it generates SHA-256, okay, of the menu file. So what exactly is SHA-256? Okay, it has a variety of functions here lah. Okay, so I'll try to cover as much as I can. So hash function row, okay, it does take input data of any size and produce a fixed 256 bit. Okay, in this security feature or HMAC, okay, is combined with a secret key to generate a unique code. Okay, it also provide unique protection, okay, by hashing the message together. Alright, it ensures that even a single bit of change in the message, which is the hash, will completely produce a different output. Okay, this makes tampering immediately detectable. Okay, it also provide authentication. It goes hand in hand because the secret key is required to generate the correct HMAC. Only parties who share the key can produce or verify the code. This will allow the authenticity to be achieved. Alright, so collision resistance as well. SHA-256 is designed in a way to make it computationally infeasible for attackers to find two different inputs that produce the same hash. This will strengthen the reliability of HMAC. Okay, in general, the efficiency and security is increased. It is widely adopted also because it balances strong cryptographic security with efficient performance. Okay, it is very suitable for the real world systems, right? Like our spam tool. So the server will send both the menu and its HMAC to the client. Okay, on the client side, okay, this time we have to go to the client side. Okay, it's easier for me to start there. The function receive menu secure data. Alright, it will recalculate HMAC and compare with the received one. Okay, why HMAC? Okay, as we just now explained about SHA-256, it actually covers majority of the key features of why HMAC is very important. Okay, first it ensures integrity. Okay, ensures authenticity also. Okay, this will in turn prevents attacker from injecting fake menu items or corruptible data. Yep. So okay, we'll move on to section 3. Okay, we call it the ECC. It's also the elliptic curve cryptography. Okay, nowadays it is the backbone of various various secure key exchange and digital signatures. Okay, we start with the server side. I need to explain the server side first. Okay, here it is. Right. Okay, we generate a fresh ECC. Okay, to send the public key to the client. Right. So in turn, the next step, client side, they will do the same, generating a private key and sending the public key back. So for this one, client side, it will be here. Yeah, so they will do the same, generating a private key and sending the public key back to the server. So both sides then now will perform the elliptic curve Diffie-Hellman ECDH. Right, so back to the server side. Okay, there will be a command here. Alright, this is the line that actually performs the ECDH to derive a shared secret. Okay, it uses the function called the server private data. Okay, with the client public point. Okay, for this one here. Okay, then for the client side also have one. Okay, the client side is right here, so it will be this one. Okay, it will derive the same shared secret. Okay, both arrive at the same shared elliptic curve point. Okay, from this point they derive a shared secret and then a session key using the SHA from the HMAC side. Okay, we also do use ECC for digital signatures. Okay, in the line 82, okay, which I can see right here, I push it down a bit, which is the signer sign. Okay, the signer sign function, okay, it signs the encrypted sales data with its private key. Okay, of course, client side is done, server will do the verification. Server will have their own code. Their code is called verifier verify. And that concludes, because it verifies the client's ECC signature to ensure the authenticity and the integrity. So the ECC is complete. After three types of codes that we just talked about just now, which is the first one, they generate the ECC, right? Then after that, they follow by the computing, which is the server private data, and both sides will have to reach the same elliptic curve point. Then finally, they will do the signing from client and verifying from the server side. Okay, so particularly ECC. Why ECC? ECC has a much more higher advantage than RSA. They are actually similar, but they provide the same strong security as RSA, but with smaller keys as compared to RSA. Alright, they also provide authentication, alright, with the signatures verification, integrity, okay, and confidentiality with ECDH. Sorry, I cannot remember the very long name. Wait, the ECDH, the name is too long. I cannot remember. Sorry. So okay. So it is very very efficient for ECC for modern systems, especially mobile and IoT. Okay. So the last point and the most recent one that we added in order to make it more robust, okay, is actually called the perfect forward secrecy, the PFS. Alright, so this one we'll just touch on, because actually with all these three, adding this is just in one point a bonus, right? So for that, okay, PFS, perfect forward secrecy, after I do some checking and some research, okay, PFS actually ensures that the communication sessions will remain secure, even if the long-term keys are compromised in the future. In both of the client and server systems, the PY systems, the Python code servers systems, okay, fresh ECC keys are always generated for every session. Okay, it will produce unique shared secrets and unique session keys through the elliptic curve Diffie-Hellman. Yeah, I think I got it already. Okay, because all these keys, these private keys, are discarded after use. Past encrypted data cannot be decrypted, reused. So this will generate long-term confidentiality. Even if the attackers gain access to the server's private keys later, they cannot unlock because the previous are already discarded. They will not be able to get the new ones, which ECC is actually working on. Okay, this particular security feature, we call it the PFS, actually works as a safeguard against intrusions by preventing replay attacks, mass surveillance, and certain kind of decryption. Maybe I'll call it, what's the word for it, retrospective. Yeah, so it is going to be a critical layer of resilience in various modern secure systems nowadays. So how it works, actually, as I explained earlier, every run of the program will produce the unique shared secret and session key. So even if an attacker compromises it later, okay, they cannot decrypt past communications. Okay, so each session will discard their own keys. It will ensure long-term confidentiality, okay, and it will also protect the sales data and keep it secure even under future breaches. So to summarize, okay, AES is a security key feature that secures sales data with confidentiality and integrity. So while HMAC will protect the menu file from being tampered, okay, ECC will enable security key exchange and digital signatures. Okay, PFS, of course, I won't say guarantee, but they will work very close to perfection. Okay, that past communications will remain safe even if the future keys are compromised. Okay, so together, all this mechanism, they will form a very robust security framework for our client server system. Okay, this project will definitely demonstrate not only the implementation of cryptographic primitives, but also what the real world is actually using, all right, in securing their business transactions. Okay, so sorry for the long talk, but we really have to prove how we work the code. It actually took us some time to actually see what we can implement for this. We want to give it our best shot. So for the next slide, okay, we will go on to future implementations. All right, the possible future implementations, which I will touch on a different slide. We will go back to the PowerPoint slide, which will be provided. Okay, so I will stop the Visual Code Studio. Thank you.